In this lesson, you all are going to learn about what a mole is. A mole is a new unit of measurement we're going to learn about, and it's a way for us to measure very large numbers of things. A lot of times in chemistry, we're working with very small things like particles, and so a mole is a convenient way for us to represent these. Just like how we count shoes in pairs and we count eggs by the dozen, we count atoms and molecules in moles. So it's just a quantity that describes a certain amount of things. So we need to have this new unit because matter consists of incredibly large numbers of atoms. A mole is equivalent to 6.02 times 10 to the 23rd atoms. This is an important number for us to know. So if we take a look at what this actually represents, if you think about a piece of copper that's 1 centimeter by 1 centimeter by 1 millimeter, a centimeter is about this big and a centimeter is about that big. So we're looking at a tiny, tiny little piece of copper. It's so small that you almost can't even see me showing you how small it is. And that piece of copper approximately contains 5.1 times 10 to the 21 atoms, which is a huge, huge number. So we need a way to quantify these easier. So the mole was defined on the number of atoms in 12 grams of the isotope carbon-12. So not the average carbon, but average 12, the one that weighs 12.0 grams per mole. So what scientists did is they defined it based on a quantity. So 12 grams, so 1 mole is equal to 12 grams of carbon-12, and the mass of each of those atoms, they found the mass of each of those atoms, and they're saying that it's 1.94 times 10 to the minus 24. This is an extremely tiny number per atom. So they have the mass of each atom of carbon-12, and that is 6.02 times 10 to the 23rd atoms. And so this is what we call a mole, is this 6.02 times 10 to the 23rd. The unit on this is pretty important. So here it says atoms. This is atoms per mole. So one mole is equal to 6.02 times 10 to the 23rd atoms, which means that if we are conducting unit conversion with this new unit, that for every 1 mole, we have 6.02 times 10 to the 23rd atoms. You could also flip it around. You could say for every 6.02 times 10 to the 23rd atoms, that's inside 1 mole. So this is how you'll use it in unit conversion. So remember that this is the same thing as both of these down here, and you can use it either way depending on what unit you're trying to solve for when you're using this in conversions. This number is known as Avogadro's constant, or Avogadro's number, you might hear me call it that. And it's 6.02 times 10 to the 23rd. Something else we need to pay attention to is it's not just atoms that this describes. It also describes all kinds of particles. So we could be describing electrons. We could be describing protons, neutrons, particles, any type of thing that is itsy bitsy small. We can use a mole to describe it. So it doesn't have to be just atoms that we're talking about. It can be any type of subatomic particle that is very, very small as well. In addition to using moles in chemical equations, we also use them on the periodic table. So if you go to your periodic table, so on your periodic table, you have these numbers down here, right? And these are the average atomic masses of these elements under here. These have units on them, and the unit on the periodic table, the mass unit, is grams per mole, per 1 mole. So the molar mass of chlorine is 35.45 on the periodic table, which means that's 35.45 grams in every 1 mole of chlorine. This is a very important unit to memorize. You all will need to know this. Be very careful when you all write things. If you see grams / moles like this, we abbreviate mole as MOL. Be very careful to remember that this is the same thing as grams over moles. Please do not get this confused. This is a very common mistake students make, and I don't want to see you making it. They'll do unit conversion, and they'll think this is 1 unit and put it all on the top or all on the bottom. I'd write it like this. I would highly recommend never writing it like this, just so you don't make mistakes. So let's try this in action here. If we actually want to use this number for calculations. This problem here is asking us to find how many moles are present in 2.5 grams of potassium bromide KBr. So we want to find moles. We're solving for moles. All right. And we know that we have 2.5 grams of this chemical, 2.5 grams of KBr. This is where we need to use our new unit in grams over moles, or grams on top of moles, right? So you'd head to your periodic table and you'd look up the molar mass of potassium, which is 39.098. So 39.098 for potassium. Bromine is 79.9. So if we wanted to know the mass of KBr, we need to add these together. So we'd add these two numbers, which gives us 118.99. So you can just round that up. And that's in grams over moles. So for 1 mole, this is how many grams of KBr there are, which lets us convert. So now on our unit conversion step here, we want to solve for moles, so moles has to be on the top. We have grams here, so we need to divide by grams in order to remain with moles in our answer, because we want the grams to cancel out. So you need to remember that the number that you get from the periodic table belongs to the grams. That's how many grams are in 1 mole. The mole's really big, right? So you don't want to put the 1 with the grams and the number with the moles. That would be incorrect. Inside of 1 mole is all of these grams. As you work, you'll see that your grams cancel out. So your units are correct. We're left with moles here. And then you can simply put this in your calculator as 2.5 divided by the 118 number. That leaves us with 0.021 moles of KBr. Let's try the reverse of this problem. So if you wanted to measure out 0.035 moles of sodium chloride, how many grams would that be? First things first, we need to know the mass of sodium chloride, which means going to your periodic table. So go ahead and go to your periodic table and look up the mass of sodium and chlorine and add those together. And we'll put that mass on here. Okay, so go ahead and pause the video and do that. There will be a quiz question that we'll ask you in a second. So sodium on the periodic table comes out to like 22.9 something, so it's 23. It rounds up to 23. 2.99. Chlorine is 35.45, which gives us 58.45 grams over moles. So our next step here is to find out how many grams that this number of moles can be. So we need to set it up in a way that we're solving for grams this time. We're finding grams. We're headed to grams. We have this conversion factor, and we know how many moles that we're starting with. Okay, so see if you can solve this one on your own. There will be a quiz question that asks you about this, so feel free to write this down. In order to solve this, we need to use the conversion factor that we found from the periodic table. need to remember that because moles is in the numerator here, it must be in the denominator in order to cancel it out. We also want grams in the numerator because we're solving for grams. We don't want that to cancel out. So our moles is going away. Excellent. So our units are in the right location. Now we need to make sure that our numbers are in the right location. So remember that any mass from the periodic table is a certain number of grams per 1 mole. 1 mole. So the 1 belongs to the mole and the number belongs to the grams. That means if you wanted to measure out 0.035 moles of NaCl, then we're going to need to measure out 2.046 grams on a balance. We use this in the lab a lot because we need to obviously measure out certain quantities of chemicals, and we use our molar masses a lot to calculate what we need to measure. Let's take a look at molarity. Molarity is another important unit that we need to learn about that we use in chemistry like a lot, all the time. I'm always using molarity. I think I use it sometimes more than grams per mole. So molarity is a concentration, and it's measured in moles over liters. We're seeing this new moles thing, right? So moles over 1 liter. Remember this slash? Remember how I told you to be very careful about how you write this? So make sure that you write it as moles over 1 liter. I would not put them both on the top. And this is our new unit. This is called molarity. We also need to understand a few more definitions if we're going to talk about concentrations. So concentrations normally refer to solutions. Solutions are homogeneous mixtures of 2 or more substances, and the things that they're normally comprised of are a solvent and a solute, and those 2 things make up our solution together. The solute is a component in a solution that's not the solvent, so it's usually the thing that you're putting into the liquid. So you can see an example here of sugar being put into the liquid, into water. In this case, the solute is the sugar. The solvent is the component of the solution that is present in the greatest amount. It's usually what you're dissolving the solute inside of. So in this case, it would be the water. So we've got water, sugar, right? A solution may contain 1 or more solutes. You could put sugar and salt in water, right? And they both dissolve, and your solvent is still water. So keep that in mind. If you ever hear me use the term aqueous, an aqueous solution, this is just a chemistry way of referring to water as the solvent. So if you hear that, that's what that terminology means. We have a lot of different types of common solvents. Water is obviously a really great one, but we use them for different types of applications. So if you think about paint thinner, right? We use paint thinner to thin paint because paint is not soluble in water. We have to dissolve the paint in something that it dissolves in. Oil as well is another type of solvent that can be used. If you are doing paints and you have oil paints and you want to dissolve them in something, we can't do that in water. So that's an example of solvents being used. In order to visualize a mole, I kind of like looking at it this way. So we have a certain amount of moles inside of a liquid. So moles per liter. And let's assume each dot is a mole. It's not, obviously, moles are not dots, but let's just assume. So in this scenario, we've got 1, 2, 3, 4, 5, 6, 7, 8 moles. 8 moles. In 50, let's assume this is milliliters. So if we wanted to know the concentration of this chemical, it would be 8 moles per 50 milliliters. Because molarity is defined in liters, we do need to convert the milliliters to liters. So milliliters to liters. So if we have 50 milliliters and we want that to liters, we know that inside of 1 liter is 1,000 milliliters. Unit conversion tells us that our milliliters needs to be on the bottom and our liters needs to be on the top in order for these to cancel. And we know that there's 1,000 milliliters in every 1 liter. So 50 divided by 1,000 gives us 0.05 liters. So the concentration on this first beaker, if we were to calculate, would be 8 over 0.05. 8 moles over 0.05 liters, which gives us 160 moles per liter. You'll notice I wrote this as a capital M. That is how we abbreviate molarity. So you need to be really careful with your M's, right? We use the letter M for a lot of abbreviations. We use it for meters. We use it for milliliters. We use it for moles, right? And now we're using it for molarity. So be very careful about how you abbreviate the M because it appears multiple times. So I'd recommend using capital M for molarity. Now this example is not great because this number 160 molar is something that you'll never ever see in real life. That number is crazy high. Molarity is usually lower, so usually like 1 molar or below. But I just use this for demonstrations. So let's see here. Let's check out this other one, right? We've got 1, 2, 3, 4, 5, 6, 7, 8 moles. But now we've got a reduced amount of volume. Now we only have 25. Let's say this is 25 milliliters. That's half the volume, all right? And so this would be 0.025, which is now going to give us, it's going to be twice as concentrated. So we're going to see 320 here instead because we cut the solvent in half. So a lot of times we'll use a technique like this in lab to reduce concentration. So we go from a stock that has a high concentration like this, and we'll cut it in half, right, to make it weaker so that's easier or safer for us to work with. This is why molarity is really important. So here's how we use this in practice. Generally in the lab, what we'll do is we'll measure out a solid on a balance, get that mass, and then we're going to put that into a flask like this. This is called a volumetric flask. You might want to write that down. You'll hear me use that term a lot in the lab. It has this narrow mouth, which makes it very accurate for measurements. And we'll put that solid into the flask, and then we'll put in the solvent, in this case, which is ethanol. And then it's filled up to the mark here. So we're just filling it up. They're showing you how they're mixing it and they're filling it up. And so now we've made a solution at this point, right? We've got our solute, and our solvent that we've dissolved it into. So let's calculate the molarity of this solution. Given that we have 10 grams of cobalt chloride dihydrate, that's what that represents. The di is the 2 here, dihydrate, that's the water. There's 2 waters attached to it. COCl2, okay. And we want to find the molarity. So our molarity, remember, is in moles over liters. That's where we're headed. We can see here we have 500 milliliters. So we know the volume as well. So we've got this. We have grams, and we know previously that we can go from grams to moles, right? We can do this conversion. So we're going to end up with moles, and we know we can take our 500 milliliters and convert that to liters. So we're going to do both of these things. Now this problem gives you the molar mass of cobalt chloride dihydrate. I'd like us to calculate it together. I want you to see how this is done. So it's very important that when you're calculating these masses that you're adding them up properly. So cobalt, you need to go to the periodic table. We have 1 cobalt. We have 2 chlorines because the Cl2, there's 2 of them. We have a dihydrate. We have 2 of these waters. So we have 2, you can assume this is in parentheses, H2O. So that means that we've got 2 hydrogens, and we have 2 of those molecules, right? So we have a hydrogen, oxygen, hydrogen, and we've got 2 of them. So in reality, because we have 2 of these molecules, we've got 4 hydrogens, all right? This 2 is being distributed. And we see that with the oxygen as well. We're going to have 2 oxygens, so 2 oxygens. So let's head to the periodic table and add up these masses. So go ahead and go to your periodic table and write down the masses of each of these, and we'll come back. Okay, so these are the numbers you should have from the periodic table for each of these elements. We need to be careful to make sure we multiply them properly based on how many we have. We've got 2 chlorines. We've got 4 hydrogens. Remember, this is a 2 times a 2, so times 4. We've got 2 oxygens, so times 2. So we'll add all of these up. All these get added up together. We'll do this first here. We'll multiply them, and then we'll add them all up. So 58.93 plus the 35, so that's going to put us at, then we're going to have 4.04 and then 32. We're going to add all these together. It's going to leave us with 165.87. Okay, so then that means this is incorrect. Oh, goodness. Okay. It could be that this number here, the 170, was for a different chemical, maybe cobalt-1 chloride or cobalt-3 chloride, not cobalt-2. So don't take heart to that number being different. This is the one we want to use. Okay. And what unit is on this number? Anything on the periodic table is going to be in grams per mole. So be very careful to write that down whenever you pull that number off the periodic table. I'm going to go ahead and erase this so we have a little bit more room to work, so feel free to pause if you need to write this down. Okay, so let's do our first step and convert grams to moles. We want to get to moles here. We know that we have something in grams per mole. We have to be very careful about where we place our units. Remember, the grams needs to go away, and we want to end up with moles. So anything divided by itself is 1. So if we've got grams on the top and the numerator here, then it must be in the denominator. Inside of 1 mole are 165.87 grams. And that's why we can write it that way. So then you put this in your calculators, 10 divided by 165.87. You'd end up with 0.06 moles. We're not done here yet because it wants the molarity, and molarity is in moles over liters. So we've got the mole part figured out. Now we need to deal with the liters. The liters comes from this volume, this 500 milliliters. So we need to convert that to liters. So if we have 500 milliliters and we want to get to liters, unit conversion, we need to cancel the milliliters, so it's going to go on the bottom. Liters goes on the top because we want to end up with liters. So we've got these in the right location because they're canceling. Now, in order to figure out which numbers go with the milliliters and the liters, we need to remember our prefixes. We have our base unit, in this case, which is liters, and milliliters is going to be 1,000 times smaller, 1,000 times smaller than that. So inside 1 liter are 1,000 itsy-bitsy milliliters. So be careful with where the 1 and the 1,000 go. So 500 divided by 1,000 is going to give us 0.5. Now we can just put these numbers over each other. We can combine these. So what we'll do is we'll put the 0.06 moles, and we're going to put that over our 0.5 liters. This is the unit we want to end up with, moles over liters. And that gives us 0.12 molar, capital M, not lowercase m. Okay. This is a much more reasonable molarity. Molarity should be a smaller number, usually less than 1. Let's see if you can practice this. Let's try this question. So if this amount of calcium chloride, the 16.43 grams, was added to 100 milliliters of water, what would its molarity be? So try this one on your own using the methods that we showed. You'll need a periodic table to look up your calcium and your 2 chlorines to find the molar mass. And you're going to need to convert this to liters in order to be able to work with it. Don't forget your units on molarity. Moles over liters, that's where you're headed. Okay, so here's how we solve this problem. Calcium and chlorine on the periodic table, we're going to need their molar masses. Calcium is 40.078. Chlorine's 35.45, but we have 2 of them, so we got to multiply that by 2. That gives us 70.9, and we're going to add the 70.9 and the 40, I'll just put it here, 40.078 together to give us 110.978. Excellent. And the unit on this is grams over moles. Very important. So we have grams, so let's go ahead and get it to moles. 16.43 grams. We want to get to moles. We're headed to moles. We're going to orient grams on the bottom, moles on the top, because we want our grams to cancel out. They need to go away. And we know that inside 1 mole, there are 110.978 grams of calcium chloride. So that gives us calcium chloride. So 16.43 divided by the 110.978 would give you 0.148 moles. We're not done yet. We've still got to deal with the liters situation. So we've got 100 milliliters. We need to get that to liters. We know that milliliters has to be on the bottom because we want it to cancel out. Liters needs to be on the top because we want it in our answer. It should not cancel out. So milliliters canceling, excellent. Let's make sure we get our numbers in the right location. So milliliters are 1,000 times smaller than a liter. That's your base unit. So in every 1 liter, there are 1,000 milliliters. Milliliters are only about this big. A liter is like this size. Big liter. So inside of one of this are 1,000 little milliliters. So 100 divided by 1,000 is going to give us our 0.1 liter. 0.1. So we can combine these numbers now. We can combine this number and this number to make the moles over liters. So it'd be 0.148 moles over 0.1 liters to give us 1.48 molar, moles over liters. We'll do more example problems of this in class.